All right, so you said I'm Ken Crane. I work with the Army Corps of Engineers at the Engineer Research and Development Center. And my topic this morning, or this afternoon, I guess, is looking at kind of how we can open the door to novel reinforced materials for blast design. So to give kind of an idea, my overview, I'm planning on looking a little bit at the current code limitations, kind of what some of these new materials are, how they can be potentially beneficial to future designs, what the barriers are to implementation, kind of how I see a path forward in that. And then also I want to talk a little bit at the very end, a little bit about the update of UFC 33401, which is the design and analysis of hardened structures for conventional weapons effects. All right. So one of the things that is problematic in our current codes is, depending on which code you use, you are limited to between 6,000 and 13,000 PSI. And it doesn't just change with code, it actually changes with section of the code. There are actually some codes where in one area you can use up to 13 KSI, but then another area you're limited to something much lower. So it's a little bit problematic, and it's also difficult because with ultra-performance concretes, we're seeing values up into the range of 30,000 PSI. I would say for structures and concretes where there's no specialized thermal curing, even, you're still seeing strengths up to the 18 to 20,000 PSI range. Potentially more important is that fiber effects are not considered. So the fiber allows for significant tension to be created in the concrete, and also significant amount of ductility. So in order to kind of highlight that, you can see over on the right, I've got two sets of tests. One, these are identical test specimens, other than the fact that one of them has fibers and the other one does not. Actually, one second. This really is the worst way to do this, but yeah. So actually, so if you're looking at the upper, that is a fiber reinforced with no shear stirrups, and the bottom is a non-fiber reinforced with shear stirrups. So you can see the significant change in the ductility, or rather the deflection, which is an indicator of the ductility between these two test specimens. So clearly our existing codes don't capture any of that additional ductility, and in fact would argue that the top should be significantly less ductile than the bottom. All right. So these new materials, as I mentioned, may have significantly higher strengths, also much higher volumes, significantly high volumes of fiber. And the tension capacities can be quite significant. The upper right-hand graph shows some different UHPCs, a couple, one that we developed in-house at ERDC, and another that's Ductil is a commercially available product by Lafarge-Holcim. And you'll see that based on a direct tension test, we're seeing strengths between 1.5 and 2.5 KSI. So this is this is where we're getting tension strength, direct tension strengths that are approaching the range of kind of what we think of as the minimum level of compression strength for concretes. And that certainly can be factored into design very beneficially. The other aspect that I want to point out here is that in this direct tension test, we're seeing strains of 0.02, and this is on a test specimen, I believe, that's about 18 inches long. So it's really a crack, or it's an aggregated crack opening more than it is a true strain, because it's not fully distributed. But nevertheless, you're seeing a post-cracking behavior that is very ductile. And there's I believe, a large potential benefit to using that kind of ductility in blast designs. So finally, looking also at steels, we have some steels with yield strengths up to 120,000 PSI. There's very little data being done. There's very little data in the literature so far on how these materials perform at higher strain rates, which is a limitation to them being used in blast design. I do show over here on the right, this is some of the only data that I was able to find, and it's a little bit problematic for us civil engineers because it's presented in terms of a true stress, true strain, and none of us like true stress, true strain. But what I do want to point out, in yellow and purple, we have the high strain rate behaviors of these materials at 7,000 strain per second and 3,000 strain per second. So there is some preliminary data that does show some significant dynamic increase for these very, very high tensile capacity materials. Potentially problematic is that, actually that's not true. I was going to say that there was not enough ductility on the 700 strain per second, but it was actually unloaded rather than being fully tested to failure. All right. So the potential benefits of using an ultra-high-performance concrete could be that there are significant reductions in steel requirements. You saw from Bill's presentation the incredibly congested sections and the difficulty that comes with those. So imagine the increase in constructability and labor cost if you were able to remove a significant amount of that shear reinforcement from your design. Also, these that may be further increased by these high-strength steels that may reduce the required reinforcement ratio for the traditional steels. Now, of course, there's more research that needs to be done with this of what is the effect of actually having a broader spacing of steel. Are there lower ductilities for some of these steels particularly? So I'm not suggesting for everyone to go out there and spec 120 KSI steel tomorrow, but I do think there's significant opportunities for particularly increasing constructability of blast-resistant designs using these materials. So I think the increased ductility, in order to really make use of that, we're going to have to rethink some of our response limits. Right now, a lot of our response limits for concrete construction are based out of World War II bombing reports. We base what we consider to be our acceptable rotations at failure from a design perspective on what we saw in London in the 40s. So particularly for materials that have much higher ductility, I think these can significantly be updated to allow for increased benefit from these materials. Right now, if you were to design with this material, you would still be limited to the same support rotations that are required for other concrete structures, and you would essentially be hammering your square peg into that particular round hole. So another interesting thing that may occur there is as you do begin to have larger amounts of allowable ductility, now you're beginning to engage other types of actions in the structure. You're no longer just looking at bending in this. You're actually engaging a full membrane action in your members, which can actually have very different effects, both positive and negative potentially, on the rest of your structure in the direction that loads are being applied in a blast environment. So there's significant study that needs to be done there to really understand those mechanisms and how they can be beneficial or detrimental depending on the case. So the durability of protective structures may also be increased significantly. Ultra-high-performance concretes oftentimes have permeability to salt ingress, approximately 100 times that of normal strength concretes, particularly when we're looking at hardened structures, which are often underground in constant contact with groundwater. Those who have, anecdotally, there are lots of hardened structures that have problems with water intrusion because of issues with the concretes. These are potential benefits to ultra-high performance concretes as well. Also, decreased allowable cover in general for protective design. We don't think too much. Our cover is really just for, I won't say it's just for, it adds mass, but it is primarily for environmental protection. We really are worried about the distance between our inner and outer steel cages. If we can reduce the amount of cover necessary, this provides an additional economic incentive to using some of these materials with much higher environmental resistance. Some of the current barriers to implementation are the lack of guidance. Certainly, we have the ACI 239 Ultra High Performance Committee that I'm currently missing that's working on design guidance as well as materials guidance. We have, and I obviously didn't do my homework and actually look up that ACI, so it is not actually indeed ACI AKS DJF, so nobody take note on that. And again, there are many research needs still, specifically those unknown dynamic loading effects and the structural response limits. So what I see as a path forward for this is really kind of a tiered approach. There are only so many things that this, as I see it, the role of ACI 370 is primarily education. And I say this because we have the ability to have an open distribution location to introduce some of these ideas of novel materials. And I think in doing that, we can create interest in application of the materials that will drive the industry, particularly in the blast design world. I think we can do that through things like sessions where we disseminate new research, and additionally highlight what needed R&D there is out there. I think another thing that needs to be part of this path forward is the update of the PDC 0608 that is ongoing now, looking at some of these response limits and saying, all right, can we get larger ductilities? Can we allow for these significant displacements in these new materials that may allow for their more effectual use? Then finally, I think that a lot of this, at the end of the day, may end up having to go into the update of UFC 34001. This is the design and analysis of hardened structures for conventional weapons effects. It is a limited distribution document owned by the U.S. government, and specifically it falls under the purview of the Chief of Engineers within the Army. It's a tri-services manual. It has been approved for a major update. Myself and John Geringer and a few others have been working on this for the last 5 or 6 years, and we have finally received funding to spend the next 5 years doing a significant overhaul of this document. Those of you who are in the blast design world are probably familiar with this document and know that the last time it was updated was 1998. There was a new cover slapped on it in 2002. So what we're hoping to do is to actually include for the first time some actual methodologies for UHPC. So specifically, we already have data in hand to adapt the existing breech spall curves for higher strengths of concrete and UHPCs. We also have some updated material models, specifically kind of the stress strain curves, post-peak behaviors, et cetera. So the last couple of slides I'm going to spend just kind of looking over that update, because I think it's pertinent to a lot of the people here, and I think just knowing about that update is important. So the things that we hope to do with this update over the next 5 years are kind of modernize these with kind of the modern structural engineering approaches that we've created since 1998, including a modern design basis with a better understanding of response criteria and asset fragility. Updated threats. Clearly, our weapons on the U.S. side have changed significantly in the last 25 years. We can imagine that those countries that we think might be adversary actors have probably also increased or changed their weapons capabilities. We want to actually be able to simplify the code and specifically increase the references and correct those places where there are errors in the existing code. And finally, incorporate a lot of the R&D that's gone on in the last 25 years. I mean, you have to remember that 1998 was pre-9/11, so that just our understanding of the world and maybe blurred line in some ways between what previously would have been very segmented as ATFP and what is conventional weapons, that line really changed on 9/11 in a lot of ways. So those are some of the major update goals. And so kind of the organization of the update is that we use criteria change requests, same as 33402, where anyone can actually put in a request that says, I think that this particular section is inaccurate or insufficient. And those can be input by consultants, other government folks, academics. Anyone who has access to the document can put in a request to change that criteria. That doesn't necessarily mean all requests will be followed, obviously. Based on those, we're hoping to update the content for both its relevance, its rationality, and its consistency across the entire document. And then the way that we hope to product that is to produce a product there is a final UFC, but also in the process really kind of a reorganization and technical update. And some of that may be released kind of incrementally in ECBs, which are engineering construction bulletins, that are kind of a methodology we have for releasing some of these sections without having to essentially send the entire UFC through the heads of the Navy, Air Force, and Army that it will eventually have to be approved by. I know that many of you may be interested in that. Because of that, I've included down at the bottom the main point of contact for that is John Geringer. He's with the Army Corps of Engineers Protective Design Center out of Omaha, and he's kind of been heading up. The Protective Design Center owns this document, and so they're heading this, and ERDC is kind of providing some of the primary technical support, but we're hoping to engage people across the community in this process. So that's all I've got. Hopefully I didn't put us any further behind, but I've got maybe time for one question. Is that okay, Ganesh? Anybody? All right, either I was perfectly clear or everyone is asleep, and I'm okay.
Thank you.
Thank you.